Okay, so this video is again still 2-1 and 2-2 notes, but we're taking a look at the page. So you're going to go to the start where we had to interpret these limits as definitions of derivatives, and then come down to where you see piecewise examples. Okay, so our first job is that we want to take this piecewise function and we want to find its derivative. And at first glance, it's pretty easy that you're going to think about differentiating each piece. So f prime of x is also going to stay a piecewise function, and the derivative of the top piece is 2x, because the 2 is just coming down in front, minus 0, because the derivative of that constant is 0. And then down here, the 4 hangs out in front, derivative of sine is cosine, so 4 cosine of x. The tricky part is, at first, all you can put on there is x greater than 0 and x less than 0. And then we're going to put a note that says we must decide if it should be less than or equal to 0, or if it should just be less than 0. And the reason why we have to make that decision is because it may or may not, f may or may not be differentiable at the split point. Because sometimes split points cause discontinuities, and we saw as one of our 4 examples of where derivatives don't exist, if I have a discontinuity, that's a problem. Okay? Because if my pieces are coming together, well, if it's a discontinuity, that's a problem. Also, even if my pieces come together, but if they come together in a sharp corner or a cusp, we also saw that that was a problem. Okay, so we are going to check in order to decide if we think we have the derivative there. This is finding the slopes for us. So we're going to go back and see first of all, so first check continuity. In f, because we know if it is not continuous, that implied that it was not differentiable. So if we find that it fails continuity, the original function fails continuity, then we know that the derivative is not going to exist at the split point. So let's check continuity at the split point for f. Check continuity in f at your split point, breaking point, boundary point, whatever you call that. Okay, so in our case, it's x equals 0 here. All right, so I'm going to take the top piece. So if x equals 0, then x squared minus 2 turns out to be negative 2. And then the bottom piece, 4 sine of x, turns out to be 4 times 0, which is 0. Those don't match. So f is not continuous at x equals 0. So that implies f is not differentiable at x equals 0. So I know that my final answer is really just what I wrote in blue here without the equal to. That being said, I want your notes to be complete. If f is continuous at your split point, then you need to check for sharp corners or cusps. And how you do that, you're really checking for them on f, but a really easy way to do that is to check continuity of f prime at your split point. And if your derivative turns out to be continuous at the split point, that means the slopes are actually going to match up on each side. So it meant that you checked the original and the original matched up, so it met up. And then you checked the slopes and the slopes matched up on each side. That tells you you have what we call a smooth function where you're not going to have a sharp corner or a cusp. So I want to cover all our bases. This is an example where the continuity in f failed, so therefore it's automatically not differentiable. But if that part checked out to be true, where f is continuous at the split point, then check for sharp corners, and the easiest way to do that is to check and see if f prime is continuous at the split point. If all of those things are working out, then you could come up and you could use the equal to here in green for your final answer. So at first, your instinct for taking derivatives of piecewise functions is probably going to make sense, that you're going to differentiate the top part, differentiate the bottom part. But the tricky part is making sure that you decide whether or not you should use that equal to bar, even though there was an equal to bar in the original. There may or may not be an equal to bar in the derivative. So again, since we failed continuity of f, our final answer is that f prime of x is equal to, what do we get for the top part? 2x. And then the bottom part, 4 cosine of x. But top part was only good when x was greater than 0, and then we saw in this case for the derivative, the bottom part was only good when x was less than 0, not when it was equal to, because the original was discontinuous at x equals 0. That means it is not differentiable. That means the derivative does not exist. Okay? So that's our first example, just finding the derivative. Then we switch over, and you've seen this for AP a lot already. They want you to find values of A and B and possibly C or K or something like that to make sure that the function is differentiable everywhere. So it's your job to make sure that in the final answer you get to include the equal to bar not only in the f, but in the f prime. Okay, well, there are a couple of things that we need to check in order to make sure that that happens. So I would say first, we're going to pay attention to the fact that if it was not continuous, if f was not continuous, that implied that f was not differentiable. So our first step is to check the continuity of f. In this case, when you're trying to solve for all the letters, make f continuous. Okay? We'll have to figure out what's going to do that. So that's a review of chapter 1. We've had to find values of a and b and c and stuff to make f continuous. So let's go ahead and check. In this case, our split point is, again, x equals 0. So if x equals 0, ax squared minus 2 turns out to be a times 0 squared minus 2. That zeroes out the whole first part, so that leaves you a negative 2. The bottom part, would ax minus 3b, would turn into a times 0 minus 3b. Well, a times 0, that zeroes out as well, so you get negative 3b. If I want to make f continuous, then I need these to be equal. So if I set negative 3b equal to negative 2, that means b needs to be positive 2/3. That's one part of this problem. If I can make sure that b equals positive 2/3, I can make sure that f is continuous. Great. That, for one, finds only one variable, and for two, does not guarantee that you're going to be differentiable everywhere. So the first thing to check to be differentiable everywhere is that f is continuous itself. But the second thing to check is that we have to avoid sharp corners. corners, and cusps. And the way you do that is by making sure you're going to check continuity on or of f prime. You're going to, in this case, since we're trying to find the variables that work, you're going to make f prime continuous, because that's what's avoiding the sharp corners and the cusps, which we need to make sure is happening because we want to make sure we're differentiable everywhere. Okay, so now let's switch over. Here's f. Let's differentiate it one piece at a time to come up with f prime. F prime of x is going to be, well, for the first part, a is just a number. So if that throws you off and you don't know what to think about, I want you to think about it as if, what if it was 5x squared minus 2? If that's y, then y prime is going to be 2 times the 5 times the x, and then it's going to go to 0 minus 0. So for ours, it's going to turn into 2 times the a times the x, and then minus 0. And on the bottom, if that's throwing you, instead of ax minus 3b, what if it was 7x minus 3b? We know what that is because we know b is just a constant. So again, what if that's like 3, and I don't know, we've figured out b, so let's plug it in. 3 times 2/3. Then what would y prime be? Well, y prime would be 7 for the 7x part, and then this whole part is a number, so it would be minus 0. So in this case, it's not a 7 anymore, but instead of the 7 being in front of the x, the a is in front of the x. So it's going to turn into a when you differentiate. Minus 0 again. Okay. Then the top part would be when x is greater than 0. The bottom part would be when x is less than 0. And typically I'd be really leery of putting that equal to bar there. But I need the equal to bar. So if I switch colors again, I need this. Well, the only way I can make sure that this equal to bar can be there is if I make sure that f prime is continuous. So I need f prime to be continuous at x equals 0 to make that happen. Well, so if x equals 0, 2ax turns into 2a times 0, which is 0. A doesn't change. If x equals 0, that a part is still a. So I need a to equal 0 in order to make this happen. Okay? So what we have found is if a equals 0 and b equals 2/3, f is differentiable everywhere. That means the derivative exists at any x value you want to plug in. What that really means is that you would be looking at a function f of x equals, and if we just go back up and substitute in what we have, if we let a be 0, that wipes out the whole first term here. That turns f of x into the function with -2 on the top, and then -3 times 2/3 on the bottom. That function is continuous everywhere. Well, hopefully you say, well, yeah, that function's continuous everywhere because it's the exact same piece on top and bottom. That's not always the case, where it turns out to just be a number on top and a number on bottom, because it's not always the case that you want one of the variables to be 0. But to thoroughly understand what's going on, that's what we found for a and b. That's what that really means. In general, the process that you have to check for is making f continuous and making f prime continuous. And if you make both of those things happen, you'll be okay. Okay, let's try one more. In this case, we're finding a and c so that happens. Just checking, so I'm trying to be consistent on color. So I did green and then red and then blue. Okay, so first thing I would have to check is we know if f is not continuous, we know that means that f is not differentiable. So I'm first going to make f continuous. I have to make that happen. Well, then specifically, I really have to worry about at the split point, which in this case is x equals 2. So at x equals 2 for the top part, I get x cubed plus 4a. That turns into 2 cubed plus 4a, or 8 plus 4a. Okay. Then on the bottom part, I would get ax squared plus c. Well, so that would be a times 2 squared plus c. So that's 4a plus c. If I need to make f continuous, then that means I need these two things to be equal. So then I have to solve that out. What happens when I set 8 plus 4a, the top part, equal to the bottom part, 4a plus c? Well, the 4a's cancel out, or you subtract them on both sides and they go to 0, however you want to think about that, and you get 8 equals c. All right, that's one part of what I need. My second part of what I need is to make sure, if you go back and think what we just did, I want to avoid corners and cusps. The way to do that is to make f prime continuous. So we make f prime continuous, specifically at your split point. And so specifically here, that's when x is 2. But we need to actually take our derivative because we don't have it yet. So bring this down and I think about differentiating. Again, I'm going to think about, like, what if y was x cubed plus 4 times, I don't know, 7, and I want to differentiate. Really, all that's going to matter for y prime is the 3x squared, because the 4 times the other number is itself a constant number, and the derivative of the constant goes to 0. For that bottom piece, if you have ax squared, well, let's put a number in there. If I have 5x squared plus c, we figured out c was 8, well, then y prime is 2 times the 5 times the x, and the plus 8 again goes to 0. So this part goes to 0, this part goes to 0. But I do bring down the 2 and the 5, so in my case I do bring down the 2 and I keep the a. Okay, so f prime of x is equal to, and if I differentiate the top, I would get 2ax minus 0, but I don't really have to write that. And then for the bottom part, I would get a minus 0. And then my split point in this case was 2. I got to see which one's greater and which one's less. It was less than first. So x less than 2 and then x greater than 2. And typically I should be really leery of whether I put that there, whether I put the equal to or not. I need it here. I have to make this work, which means I have to make f prime continuous at x equals 2. Well, so in order for that to happen, that means 2ax, if I plugged in 2, would turn into 2a times 2, would turn into 4a. And the bottom part, a, wouldn't change because it doesn't have an x in it to plug in, but I would need those to be equal. So if I set 4a equal to a, hang on for a second. I'm missing something. Hang on. I don't know what I'm copying like something from part of another question and then this question. I'm really sorry. That whole derivative part is off. Hopefully you caught that and you were saying that this wasn't making sense, but that whole derivative part is off right there. I talked to you about one thing, and then when I scrolled down to the bottom of it, I was looking at the wrong example and couldn't see what I was differentiating. The top part derivative is going to turn into 3x squared plus 0, and the bottom part's going to turn into 2ax plus 0. I'm really sorry. It's back to these kind of examples. If you struggle, put some numbers in and work with it that way. So this is 3x squared plus 0 doesn't really matter. And then this is 2ax, again, plus 0 doesn't really matter. But I want to make this continuous at x equals 2. So if x equals 2, 3x squared becomes 3 times 2 squared, right? Which becomes 12. And then 2ax becomes 2 times a times 2, that's 4a. I need these to be equal. Well, if I want to set those to be equal, 12 equals 4a divided by 4, 3 has to be a. Okay? So if I let c be 8 and I let a be 3, then my function's differentiable everywhere. So what that tells me is that f of x equaling the x cubed plus 4a, so plus 4 times 3, and then the ax squared, so 3x squared, plus c, so plus 8, that function is differentiable everywhere. X less than or equal to 2 on the top and greater than 2 on the bottom is differentiable. I can't spell, sorry. Is differentiable everywhere. I'm really sorry I mixed up, like I just read the wrong thing and I couldn't see the formula to catch myself. So I'm sorry for the mix-up as far as the derivative. But the process is the same. I need to make sure that the original function is continuous, because if not, then it's for sure not going to be differentiable. And so I check the original function at the split point. Then I need to avoid sharp corners and cusps. And so I make sure that that happens by checking continuity in the derivative and making that work out. It's just an extra step from chapter 1, because you want it to be differentiable, not just continuous, so that makes you take a step further to check it. Okay, so that's all there. I'll do a separate little one of just kind of some announcements.